Hello and welcome to ECE 3030. So in this video lecture we will be starting to talk about sequential machines. Now in the previous video lectures we have looked into the fundamental building block of the digital systems, that is the transistors, and then we also studied the inverter, and in doing so we understood the different physical aspects, for example area, power, energy, all these things. And then when we talked about the inverters, we saw how the continuous values of voltages are representing the discrete logic values of 0 and 1. So basically a certain range of voltage represents a logic level 0, and this another range of voltage represents logic level 1, and that essentially by that what we are doing is we are discretizing the voltage to represent the discrete logic levels. Now the purpose of studying the sequential machines is to provide this next layer of abstraction in digital systems, where time is not considered a discrete continuous variable, rather time is dealt with in a discrete manner. In other words, through the study of the sequential machines, we will develop the concept of discrete time in digital systems for higher levels of abstractions. Alright, so let's get started with a very brief description of the Turing machine. So Turing machine is one of the most celebrated concepts in computer science, computer engineering. So essentially this is an abstract mathematical model of computation that was invented by Alan Turing in 1936, and the idea is simple. So it's shown with this picture on the right. Essentially what you have is a tape which is infinitely long, and then you have a head that is shown by this one, and then you have a control machine. So what it essentially does is that this head reads what is written in the tape, and then based on the state of the system, the control and the input, it moves on to a second state, and then the head moves right or left and writes something on the new cell. Now what is interesting is that this model is very simple but any computer algorithm, the Turing machine can actually simulate that algorithm, and based on that there is this concept called Turing completeness, which essentially says that if you have a set of instruction and if it's Turing complete, it will be able to simulate a Turing machine, and most of the programming languages are Turing complete, meaning that they are theoretically able to perform any tasks that a Turing machine can do. Now one of the important things here is that in the Turing model of computation, the length of the tape is infinite, but in reality such an infinite tape is not possible, but for all practical purposes the memories in our computers are large enough that it can be considered infinite. Alright, so now the important thing is that Turing machine is extremely simple. So what von Neumann did was that he came up with an architecture for a general purpose computer which is essentially Turing complete for all practical purposes, and the basic structure is that you have two different units. One is the central processing unit, and then you have a memory, and what you do is that you fetch the program commands or the data from the memory to the CPU through the data bus, and then you perform the computation, and then you put back the data in the memory bank, and again for the next cycle you fetch the instructions and the memory again. So basically the most important point about a new von Neumann machine is that the computation unit and the memory unit are separated, and this is more little bit more thorough structure of a von Neumann architecture of the computing. So we'll not go into the details of these architectures, but the important point that comes out of this is that discreteness of time. So essentially in the Turing model, time is treated in a discrete fashion, meaning that all the actions happen in discrete time steps. Now remember, in an inverter or even in the transistors, the time is not discrete. So if the input changes, the output changes right away with maybe some sort of delay. But again, the change is continuous, it's not discrete. But for the purpose of higher levels of abstractions, everything needs to be represented in a time discrete fashion. Now, on the other hand, we have already seen the discreteness in logic levels. So what we have seen is that we have two logic levels, logic level 0 and logic level 1, and these two logic levels actually correspond to two different ranges of the input voltage. So we have already seen the discreteness in logic level. Now what we are going to see is the discreteness in time. Alright, so for that, the first two concepts that we need to understand, one is, those concepts are very simple again. The first one is the combinational logic, and the other one is sequential logic. So a combinational logic is just an implementation of Boolean function. For example, say you have a bunch of logic gates like this. Say you have a NAND gate, two inputs, then you have an inverter that is connected to another AND gate, and then you have another input coming in to an OR gate. So this is a simple combinational logic. So say you have A, B, C, D. Now of course the output is 0 or 1, so which is basically means that the logic levels are discrete. But this combinational logic block over here, it actually operates continuously over time, meaning that as soon as an input changes, the output will also change. Sorry, this is an O output. So in other words, the change of the inputs results in an immediate response in the outputs. There is some delay because of the basic physical mechanisms which creates a delay between the output and the input. But essentially the thing is that the combinational logic provides discrete values in terms of the logic levels, but they do not work in discrete time, they work in continuous time. Now the way to make a combinational logic into discrete time is this concept called sequential logic. And what happens in the sequential logic is that the output not only depends on the present values of the input, but also it depends on the past input, or other words, so the output of the sequential logic depends on the inputs plus the current state of the system. So, and this current system depends on all the past inputs that were put into this, and that essentially means that in a sequential logic we have a combinational logic block. At the same time, we have a memory element which remembers the current state of the system, and the general term that we use to describe a memory is a register. And essentially the output of the sequential logic will be a function of the inputs that come in as well as the current state of the system which is stored in the register, and the next state of the system also depends on the inputs and the current state. So this is usually how a sequential logic block is represented. And here the important thing is that there is a clock here, and this clock essentially says when the state of the sequential logic block will be updated. And this clock is essentially what discretizes the time, because the state of the system will be updated at each clock pulse or some sort of discrete time steps which is determined in the clock signal. So again, sequential logic creates a situation where the continuous nature of the combinational logic blocks are converted into a discrete nature, discrete time nature, through which the state of the system is updated in discrete time steps. So so you may have seen it many times before. A sequential logic is essentially represented by a state transition diagram. For example, you have the three different states 0, 0, 0, 1 and 1, 0. And if the input is 0, it goes back to 0 here, or if the input is 1, it goes from this state to that state and the output becomes 0. And all these transitions depends not only on the input that you have but also the current state of the system, and in this process it also gives out an output. So this is how a sequential machine is represented in terms of a state transition diagram. Alright, so as we have seen, generally we use registers. So register is the general term that we use to describe memories, and so essentially the output of the register is controlled by the clock. Now usually we have two types of registers that we'll look into: latches and flip-flop. Now we'll look into it more details in the next slide, but essentially a latch is a memory device which is transparent, which just changes the value of its output, changes for some combinations of the input. So that is called without depending on the clock, and if you put the effect of a clock into a latch, it turns into a flip-flop. So for example, there is an example of a set reset latch, and essentially what it does is that if both S and R equal to 1, it stores a value of 0. Sorry, if the input is 1 and 0, then it stores a value of 1, and if the inputs are 0 and 1, then it stores a value of 0, and if both of the inputs are 0, then it just holds its previous value. So that's that. On the other hand, another type of latch is D-latch, which is essentially made of an SR latch, and what it does is that if the enable signal is 0, no matter what the value of D is, it will remember its old state, which are represented by these two. On the other hand, if the enable is 1, then the output will essentially become equal to whatever the input. So if enable is 1 and D is 0, the output will be 0, and if the enable is 1 and D is 1, then also output will be 1. And this is how we usually represent a D latch. Alright, so now the flip-flop. So as we have seen, for example, in case of the D latch, it's transparent, meaning that as long as the enable is high, the output will change as soon as the input D changes. On the other hand, the way flip-flops are designed, these flip-flops are not transparent. So it changes only when the clock goes from 0 to 1 or a 1 to 0, basically edge triggered. The example that we'll look into is a D flip-flop, which is negatively edge triggered, and this is how a negatively edge triggered D flip-flop is made. So let's say, so basically you have two flip-flops. This is the master flip-flop, this is the slave flip-flop, and say this is the output. This output we call Q1. Alright, so let's say your D is like this. So before 0, there was some value of D, and then the clock. So say clock came in here. All right. So if the clock came in here, only after the clock comes in, the Q1 will be able to read the value of D. So what will happen is, until the clock was there, the Q will remain whatever state it was in before, but as soon as the clock positive pulse comes, Q1 will simply, the D will be transferred from this to this in the first edge of the clock, and then for the second D latch, the enable signal will look like this, which is the inverted version of clock. So this is the clock invert, and you can clearly understand that, say this is Q2, you can clearly understand that it will keep whatever the value of Q1 was until this edge, and after this edge this Q1 will get transferred to Q2. So that's that. So essentially what it will look like is that at the negative edge of the clock, the data goes from this to the final output. All right. So this is a negatively edge triggered D flip-flop. Again, what happens is that when the clock is active, the first latch is on, and as a result the input gets transferred to the output of the first latch. But when the clock is active, the second latch is not transparent, and as a result the input does not end up in the final output. But when the clock goes inactive, the second latch becomes transparent, and as a result the value of Q1 goes into Q2, which is the final output. And essentially in the negative edge of the clock, the output of the latch after output of the D flip-flop changes. So in other words, this flip-flop responds to the negative edge of a clock. You can also design the same flip-flop which is triggered by positive edge by putting the inverter in a different manner. Alright, so there are two important characteristics that you need to consider when designing a register, and those two important timing requirements are the setup time and the hold time. So setup time essentially means that the amount of time during which the input data D has to be stable before the clock edge arrives, and then hold time is the time for during which the output the input data D has to remain stable after the clock edge. So these are the two times: setup time TS and hold time TH. And important thing to note is that if you don't maintain the setup and hold time requirements, the flip-flop will not work properly. All right. So now combinatorial logic, combinational logic. So there is this concept of worst case delay. So for example, you have a logic block that looks like this, and here you can see that these inputs will come fast, but essentially to get the final output, you will need to wait until the inputs or until the computation is done through the entire block. So essentially this is the worst case delay, and essentially for this combinational logic, the worst case logic is determined by the critical path, and the critical path is essentially the longest path in a combinational logic. All right. So now say let's look at what are the timing, what are the requirements for the clock signal. So when we were talking about inverters, we saw that the clock period must be larger than the delay time of an inverter. But that was a very simplistic case that we saw for an inverter. In reality, we can have a much bigger combinational logic circuits, and in those cases the delay is essentially the worst case delay for that combinational logic. And to the first approximation, what you need to do is that the clock period has to be larger than the worst case delay of any combinational logic that you may have in your system. So furthermore, you as we have seen that in the memory of the register as well, you have these timing requirements of t, the setup time and the hold time. So essentially your clock period has to be larger than the worst case delay of your combinational logic plus the setup time and plus the hold time of the register that you have, and essentially that is called the clocking overhead. All right. So one way of increasing the frequency or decreasing the clock period is a technique called pipelining. So for example, in this case you have a combinational logic that has a delay of delta. Now what you can do is you can break this combinational logic into two parts, and such that the delay of each of the parts is delta over 2. Now there may be cases where you may not be able to break this combinational logic into two parts, but for the time being, let's consider that you can break the logic into two parts, and each of them has a worst case delay of delta by 2, and then in between them you add another register. And what essentially this register does is that now you see that in the previous case the final output from this register was updating once every clock period which was larger than delta. Now in this case what you will see is that there will be an output that will be coming out every clock period which can be delta by 2. So essentially by pipelining, what you are doing is that you can get more output in a given period of time, or by a given number of time. So essentially what pipelining does is that it increases the throughput, and what throughput means is that the number of results the machine produces per unit time. So for example in the previous case, by adding a register in between breaking the combinational logic into two parts and adding a register, we essentially doubled the throughput of that system. But pipelining not necessarily means that you have increased the latency. What latency means that it's a measure of the time for which an input gets converted into an output. So by pipelining, it does not mean that time the latency has been reduced. Rather, the latency will actually be increased, because by putting a memory element you have increased you have to increase the clock period to account for the setup time and the hold time of the register.